Okay, so we start. In the morning, we got to the decomposition of a matrix A. Oops, no, not this. Yeah. Okay, annotation. And let me move this. Yeah. Okay. Oh, sorry, guys. Okay, so we got to the decomposition of a matrix A into a diagonal matrix, okay? And we said that these the matrices that does the decomposition, the X inverse and X, which are the eigenvectors, okay? The eigenvectors, let's represent them by X or something. The eigenvectors goes into the columns of these matrices X, these matrices X, and these that's the decomposition of A. Okay, so this afternoon, the talk will be, or the tutorial will be based mainly on singular value decomposition, which in this case is quite similar to the eigenvalue decomposition, but also very different. So again, if I write here on my screen, we remember that, say, A was decomposed into, say, let's call it X, okay? A matrix X, another diagonal matrix lambda capital, and the X inverse, okay? And then we said that these X, the eigenvectors, we can make them orthonormal so that these matrices become how do you call it? So sorry, we can make the eigenvectors unit vectors. Yeah, that's the correct thing. And then octagonal. They are octagonal. So then these matrices becomes an orthonormal matrix Q. So then the matrix that is doing the decomposition will be an orthonormal matrix Q, okay? And the inverse here will be just the transpose. Now, what singular value decomposition is telling us is that, or what we do here is that if we have a matrix G, okay, the singular value is saying we can decompose this matrix into the product of three matrices. U, again, lambda, which also this stands for a diagonal matrix, and some matrix V, okay, which is the transpose. So then what are these U, V, and U, V, and lambda matrices? Here, say we have a G, okay? Then to do the single value decomposition of G, we do like we did in the least square problem. So we pre-multiply G by G transpose, okay? And remember that we said that this is it's a square symmetric matrix, okay? And then we find the eigenvectors. So let's use X as the eigenvectors, and let's use lambda here as the eigenvalue. Okay, so we find the eigenvectors and eigenvalues of G transpose G, okay? So we are avoiding finding the inverse as we did in the least square problem, but now we're finding the eigenvectors and eigenvalue since G transpose G is it's a square matrix, okay? So now if we find these eigenvectors and eigenvalue, let's call them, okay, let me use this notation rather. G transpose G. Okay, this is a matrix. This, say, V, it's a vector, and lambda, which is the eigenvector, this is the eigenvalue, and V. Okay, and now we have G. Then we can form another matrix. This is the minimum length matrix, which remember was G, which we post multiply by G transpose. Okay. Now this is also a square symmetric matrix, and so we can find also the eigenvalues and eigenvectors. Let's represent the eigenvectors as U, and again lambda and U. Okay. So now from this G, we have two matrices, okay, 1 and 2, which are giving us two different eigenvectors, but the same eigenvalues. This is the property of this pre-multiply and post-multiply of this matrix, okay? So the singular value is saying that the principle is that if we have a G, if we pre-multiply by G transpose or post-multiply by G transpose, these two matrices, these two square matrices, will have the same eigenvalues, but different eigenvectors, okay? So these eigenvectors are the U's and V's. So this this V is associated to the G transpose, okay? And the U's, which are the data spaces, are associated with the this is G transpose G, and this is G transpose. Okay, so these eigenvectors are associated with this matrix and this one and that. So now we have a set of vectors and eigenvalues. So say if we have an eigenvalue 1 to say n, then we'll have v1 to say vn. Wait, sorry, the sizes are not the same. Yeah. And so I have to be careful here. And then u, I think will be u to um, I think, yeah, because the sizes of these two matrices are not the same, because if G is n by m, then G transpose G will be m by n times n by m. So the size of this matrix will be m by m, yeah? Okay, and G transpose will be here n by m and m by n. So this one will be n by n matrix, okay? So the eigenvalues U associated with U will be up to n, yeah, and this will be up to m, so m eigenvectors, okay? And I think this should be also m eigenvalues of n. I don't remember correctly, but okay. So then these are eigenvectors associated with G transpose. Do I have to clear my screen now? It's complicated now. I'm going to clear the screen, okay, and just rewrite everything just as simple. So, oh yeah, no. Okay, G1, lambda 1, V1 to, I think this was up to Vm, and U1 up to UN. Okay, and so these V's, these eigenvectors will go into this matrix, okay, this V matrix, and this U goes into this eigenvectors goes into this matrix U, and then the singular values, okay, goes into the the diagonal matrix. Now I'm not saying I'm not saying eigenvectors, sorry, eigenvalue. I'm saying singular values. Now, what are these singular values? So I think it should be on the next slide. Okay, good. I think I'll go back again and then we'll explain. So let's say in the case where we're finding U, okay, in this case, we are representing by A. So A, if we post multiply by A transpose, okay, then this is a square matrix and the U's will be this, and this will be the eigenvalue, which is now this is a square of some say of gamma. Okay, what it means is, let me explain here. Yeah, because this is important. Say we have a matrix A, okay, and we say let's look at this case. Okay, so A is given by U sigma V. Oh, sorry, V. Yeah. It's so difficult to write with this. AV sigma U. Okay. And we say that if we decompose this, A can be decomposed into this. This is the singular value decomposition. So now if we post multiply this, so if we multiply A V by A V, I think I'm correct. Oh, is it correct? No, transpose. No, okay, sorry. Let's do it here. So A, I think I don't remember this. I'm trying to explain why we have the squares, the eigenvalues are coming as squares. So we can, what I mean is that if we replace this gamma square by lambda, then we have a system that is like this, a transpose, which is a square matrix, and say UIs, which are the eigenvalues, eigenvectors, and lambda UI. So that lambda I in this case is equal to gamma I square. Okay. So in this case, this will be the eigenvalues, and this parameter here is what we call the singular values. And so we see that these singular values are the square roots of the square roots of the eigenvalues. Okay, this is the take home point. This is what we call the singular values. So say if we have a matrix, I'll try to derive this later. Just let me just make this point clear. If we have this square matrix, okay, and we have these eigenvectors associated and its associated eigenvalues, then the singular value, okay, singular value associated with each eigenvector and eigenvalue is just the square root of the each eigenvalue. Okay, so these forms the singular values, and then this one rather goes into the diagonal matrix, not the eigenvalues of the square matrices. Okay, and if we go here, okay, I think I can continue. I'll try to explain this later. I don't remember. If we, yeah, so then you remember I said also that, so A transpose is also a square matrix, and it will give you the same eigenvalues. So let's replace this by lambda, and different eigenvectors, okay? And these eigenvectors goes into the V, and the eigenvalue. So since the eigenvalues of A transpose A is the same as A transpose, these are also the same singular values. Okay, so these are the same singular values. This goes and that goes here. So in short, the singular value decomposition is taking a matrix A, any matrix, mostly rectangular in our cases, and decomposing them into three, the product of three matrices, U, sigma, V transpose. Now, the take-home point here and how it's different from the if we remember the actual eigenvalue decomposition was given by, say, X lambda X inverse, okay? And we said that we can make these eigenvectors unit vectors so that these X become octonormal vectors. But then we can do the same also for these eigenvectors in these U's and the V's, so that U also and V are both octagonal or orthonormal matrices, okay? But then the good thing here is that in the case of the eigenvalue, we have only one orthonormal matrix. So the X and the X, so the X and the X transpose or the X inverse. But with the singular value, we have two actually different orthonormal matrices, okay? So this is good. This is where linear algebra gets really interesting. So we now have been able to decompose A into these two different orthonormal matrices and a diagonal matrices. And I mean, these are the best matrices you can get, because if you have an orthonormal matrix U, it means that U inverse is just U transpose, okay? We don't want to do much work. V inverse again is also V transpose. So that's why you see this V transpose. This V transpose is coming. In reality, sorry, it's here. This is the actual equations. This is what I wanted to use to derive this. I don't remember the procedures, but this should be V inverse here. We should, when we bring this here, it's the inverse, okay? But because these V's are orthonormal, it's an orthonormal matrix, we just use the transpose, okay? So this is how you do the singular value decomposition. That's why you see the definition is V transpose always. So this is the take-home point. So let me see. So we have in our system we have G times the model vector M, and equals to the data vector. And so we are doing the operation on the G. Okay, we are trying to find how we can decompose this G so that we can estimate our model parameters. And okay, I think should, yeah. So okay, the U's from this is the left. So we call these U's the left singular vectors that comes from the A transpose, okay? And the V's are the right singular vectors, okay? So it's just the eigenvalues, it's just the eigenvectors and eigenvectors and eigenvalues, but we just use these fancy names, singular vectors and singular values. At least for the vectors is almost the same. We'll see an example. But then the singular values actually is just the square root of the eigenvalues of a transpose A and A transpose, okay? So this is how we decompose A using the SVD. So this is an example of an SVD. So let's say we have A, we're trying to decompose A into U as sigma V transpose. So if A is given by this square matrix. Okay, so or any matrix, what you do is to form the matrices, the square matrices. Again, A transpose A, and uh, A A transpose. So we see that this matrix is symmetric. Okay, if we find the transpose of the whole thing is the same, and also this is also symmetric. And so once we have these square matrices, I mean, in the case where A is rectangular, this matrix are square anyway. In this case, it's simple because A is also square anyway. Anyway, we find that the eigenvalues of this matrix A transpose A is 45. The first eigenvalue is 45, and the second one is 5. So remember that we said that the singular values are just the square roots of the eigenvalues, okay? So then the first singular value will be square root of 45, and the second one will be square root of 5, okay, which is given here. So I mean, so once you have this square matrix, you use the eigenvalue, eigenvector procedure, where you find the determinant, the characteristic equations to determine the eigenvalues and then the eigenvectors as a result. And then it says here the key step is to find, okay, so we found these eigenvalues of that. And now we found the eigenvalues, okay, which are 45 and 5. And we find the associate eigenvectors. So the associate eigenvectors in relation to A transpose A. So this is given by, so this the eigenvectors, remember with A transpose A is V. So this will be V1 and this will be V2. Okay, so this is related to the first eigenvalue. This is related to the second eigenvalue. And these are not unit vectors. So we kind of divide by the length to make them unit vectors. So if we divide V1, which is this one, by the length, which is root of 2, then we set up V1s and V2s as unit vectors. And so we just here, I think in the next slide, you see the V matrix will just be then, we can bring the square root out, and V11, and this one goes into the next row, 1, 1, 1. Okay, so this will be the V matrix, we'll see. And now we have to find the left singular vectors, which is the U1s and the U1 and U2. I mean, technically you have to go through also finding, so because, okay, we know that the eigenvalues and eigenvectors of these two matrices are the same. So the eigenvalues of this A transpose will be 45 and 5, same. And then you can find the eigenvectors, okay, using the eigenvector calculations. But if you do that, usually you might run into trouble if you go through the same process of finding the V's as finding the U's. You might run into trouble. So what we do is to estimate the U vectors from the relationship. You remember we had AV equals to the singular values UI. Okay, we try to estimate from this relationship. And so if we want to find U, okay, we find them by AVI divided by the singular value. So we have computed this, we know this, we have this matrix A. so we can find the singular, the left singular vectors. So v1, this is the numerator, it's here, and then once we do the computation, we get this is the u1. Now we're dividing also by square root of 10, because we want to make this u1 a unit vector. Okay, so this is the whole thing. This is the first singular value is root of 45, and so the whole thing is u. This is u1, and this is u2, and these two vectors will go into the matrix U. So we'll have 1 over root of 10, and the first left singular value will be 1, 3, so it goes into the first columns, and the second one will be 3 minus 3, 1. Okay, and then so this will be the U, the V I wrote here, and then the sigma, the diagonal matrix, or lambda, or depending on which part I cut from, it will be a diagonal matrix where we'll have sigma 1, sigma 2. Okay, so it will be square root of 45 and square root of 5, and then 0, 0. So it's singular. Now remember that this is a linear combination, so this singular value goes with the first singular vector on the left side. Sorry, on the left singular value, because we have u. Yeah, so u sigma 1 will go with u 1, and then the row combinations will be v1. Okay, so we have sigma 1 u1 v1 plus sigma 2 u2 v2. Okay, plus. That's how you do it. So this is how you compute the left and right singular matrices, and then the singular values itself. So then we fill up the U matrix, the diagonal matrix, and then the V matrix. Okay, and these matrices, so the fun part is that these matrices are octonormal. These are octonormal matrices, so easy to do it because we can easily find the inverse. Okay, yeah, and then this is so transpose, and then this is the summation. So if we do this summation, this product, this term, we add these two terms, we are going to reconstruct A. Okay, we're going to reconstruct A. So that's what it means by singular value decomposition. Okay. Now, okay, so there's some formal definition of the singular values here. It's changed, but okay. So what it means is that sigma I is so remember that in the equation, I said we replace this by so these are the singular values, and this is the eigenvector. So because of the even power, it's going to be plus or minus. Okay, we know this. So we take only the positive square root of the singular value of the eigenvalues to go into the singular values. And it's important that once we have these singular values, like we saw here, okay, so these are the two singular values. It's important to arrange them in order of decreasing magnitude. So that's why so I mean, say we have these two singular vectors, okay, right, singular vectors. Why are we putting this as v1 and v2? Okay, we put them as v1 and v2 depending on the magnitude of the associated eigenvalue. So so the first, the higher, the one with the most highest magnitude is put first. So we arrange them in like an order of, yeah. So this two, it's greater than that. So that's how we arrange the singular values and the singular vectors. That's shown here. So we arrange them in order of decrease in magnitude on the diagonal. Okay. And then now, in the case where of course, the eigenvalues are allowed to be zero. Okay. Also, it's defined. So the singular values is, there is a square root of zero. We can compute it. This is defined. So the eigenvalues are allowed to be zero. So in the case where there are zero eigenvalues, then also the corresponding zero singular values will go at the base of the diagonal. So let's say if we were supposed to get n. Okay, these are the singular values. So this is representing the singular. We're supposed to get n singular values, okay? But say we have p up to p non-zero. These are non-zero ones, okay? And we have n minus p zero singular values. Then the first p non-zero singular values are arranged, and then we tag on at the base the remaining zero singular values, okay? And then what this implies for the U and the V matrices, left and right singular matrices, is that the eigenvectors, okay, associated with the first p non-zero eigenvalues are noted, and then the remaining p plus 1 to n eigenvectors that are associated with the zero eigenvalue or zero singular values are then also grouped. So we group the U's into UP and U naught, where this is associated with the non-zero part of the singular values, and this is associated with the zero part of the singular values. Similarly, for V, we decompose that into V1 to VP, that is associated with the P non-zero singular values, and VP plus 1 to VM singular vectors that are associated with the zero singular values, so V naught, V0. Okay, so this is how we decompose that. And schematically, what it means is that, say if there are no there are no zero singular values, so lambda 1 or gamma 1 to lambda n is not equal to 0, okay, then we can, what it means is that we can resolve all the model parameters and the data, so we can have a good association between the data space. We call this the data space, and then this is the model parameter space. So this is the V space is the model parameter space, the U space is the data space. We can resolve this, but once some of the some of the singular values are 0, then we have to really divide these spaces into two portions, where the non-zero eigen singular values, okay, non-zero p singular values, allows us to resolve only this part of the data space and this part of the model space. Okay, so then the remaining V naught, which is the part this part of the model space, we get non-unique solutions, and the V naught, we get non-unique estimates of the model parameters, while the V naught is where we cannot fit the data. So this is where we cannot fit the data. This is where the misfit is coming from. So this is what it means schematically when we have zero singular values. And then, so remember that G in the previous case was written as U, say, okay, here it's using lambda V transpose. Okay, so now if U is given by, sorry, U, P, and U naught, then the P non-singular values are, we kind of form some a submatrix for the P non-singular values, and then another submatrix for the zero singular values. Then we can decompose this also into this in this way, and then the V the non-zero V is associated with the non-zero singular values will be this and then that. So we can see that what it does is that what the zero singular values, the effect of having these zero singular values is that it knocks these U naught zero and V naught zeros off. Okay, so that we can write G as U P UP lambda P and VP. Okay, so these we can now write G just using the non-zero part of the singular value decomposition. Okay, so then this is what we mean by, this is what happens when there are singular values. So there are zero singular values in our SVD decomposition. So in effect, we get this. If there are no non-zero, then we use the whole stuff to compute the diagonalization of G. We will see later that also a very practical thing to do is that no, okay, let me just leave the one for when we get to the inverse. Okay, so here I'm just going to discuss what we call principal component analysis, SVD. PCA. So principal component analysis is just a statistical and data analysis method that we employ very often, especially in the, say, GPS data analysis and also some finances, and yeah, it's commonly used, this technique. So principal component analysis. So what's principal component analysis by SVD? So say we have some data matrix, let's call it A, okay, or for simple A naught, which have say n samples and m measurements, so m model parameters or m measurements. And what we do is to remove the mean of each row of A. Okay, we remove the mean of each row of A, such that this A now transforms into A, where this A is the mean matrix. So it's a matrix with its mean removed, so that the mean of all the rows will be centered around 0. Okay, so once we have this such matrix A, then we can make some analysis of this data. So so then the SVD finds combinations of the data that contains the most information. So we have some data in this matrix A. Okay, that's what I started with. And we remove the mean, and we use this SVD we find the SVD of this A, so that all the information, what we're trying to do is to say we want to compress all the informations into some tiny bit of more tiny bits of information. How do you say it? No, a smaller bit of information. So let's say this A is like a huge matrix, but some of the rows or columns are definitely dependent. So we want the some some parameters that contains some information about the matrix, like the full information that we need to find in this matrix. So we'll see how this is done. I think I can explain it better here. So let's say we have okay, a good example is, say we have a matrix A, which is 2 by n, where n is very large. Okay. Now remember that when we form the A transpose and A transpose A matrices, in this case where n is 2 by n, this A transpose will be a 2 by 2 matrix, okay? And the A transpose n will be an n by n matrix. So this is very large, okay? But remember that we said also that the eigen values of A transpose A and A transpose are the same. So it means that even for this 2 by 2 matrix, it will have only two singular values. Okay, so I'm just using the interchangeably eigenvalues and singular values. So it will have two singular values. And this will have n singular values, but most of them will be 0. Okay, so it means that the information contained in this small matrix 2 by 2 is the same information that is contained in this A transpose n by n large matrix. Okay, so then the question is, if say a good example is, if say A holds some matrix of some image, okay, say some image of the tree or some image of some guy, okay, and this because an image is made up of pixels, so this goes into the columns and rows of A. Then if I want to transfer this this matrix to my friend back in Ghana or somewhere, then this is a large matrix, okay, let's say a high resolution image. If I transfer all this whole thing, it's going to take me a lot of bundles taking me a lot of bundles to download. So I want to transfer some data such that the data he will download, let me call it a hat, will give him, can reconstruct this image. Okay, so I want to transfer a hat which contains all the necessary information of this huge A matrix, such that A can reconstruct the image. This image is this one, but this A contains some unnecessary information, which makes everything of this matrix so large, but it contains some very small information. The information in this A is just concentrated in some values, and these values are what are the singular values we will come to realize. Okay, all the information in this big A is concentrated in the singular values. So if I want to transfer this A to someone, I would rather transfer the simple form, okay, which is given by this singular value, so I will explain, to him, so that he can reconstruct this image rather than sending all these huge information for nothing. Okay, so this is the gist of the principal value decomposition. We have a large data matrix or large data, but the most important information in this matrix is just concentrated in some space, and these spaces are defined by the singular values of this matrix A. So if we need to transfer the A, we will rather transfer the singular values, just the singular values and the singular vectors of A, than the whole big A. Okay, so this is it. So these two singular values comes from A transpose. And we can find what we call the sample covariance matrix if we have A A transpose, okay, so this is the 2 by 2 divided by n minus 1, which this where n is the sample size. So then we go into statistics and probabilities here. So you remember that the variance you can for, say, if your sample size is not that big, is divided by n, but I mean a statistician says that it's better to divide by n minus 1. So we divide by n minus 1. So the n is the sample size, and this A. So we can form this what we call the sample covariance matrix. Okay, so that so remember when in the morning session we were talking about variance, covariance, or correlated or uncorrelated, where we define some metrics as this. Okay, so it's the same thing. It's the same metrics you get in this case. Okay. So this is the sample covariance matrix. This is how it looks like, where these quantities, so you can see here, the 1, 1, 1, 2s are just the sample variance, okay? So these are the sample variance, and the off-diagonal ones, these ones, will be the sample covariance. So how the different data correlate, okay? And if these parameters, these off diagonals are 0, then we say that the data or the samples are the variables are what, uncorrelated. Okay, so this is still the principal component analysis. So example, let's say we have this fat matrix here, which in this example is just says maths and history scores. These students are doing really bad. They're getting even minus. So in this case, if we form A transpose, okay, we can form A, and this will be a 2 by 2 matrix. Okay, we solve that because it's 2 by whatever. And then we divide by 5 because it's n minus 1. And we have 1, 2, 3, 4, 5, 6. So n is equal to 6. So we divide by 5. Then this sample covariance matrix will be given by, it's given as this square matrix here. Okay. And then this will be, so if this is, say, history, this is history, this is math score, okay, then this 40 is the variance of history, okay, of the history score, of the history yeah, variable. And then this will be the variance of maths, and this 25, the off diagonal will be the covariance of maths and history. Okay, so where a positive covariance value indicates that there is a positive correlation. Okay, and so okay, and now if we look at the eigenvalues of this matrix X, it says that they are near 50, 57 and 3, and so then we can find the how do you call it, the singular values. Remember, the singular values are the square roots of the eigenvalues. So the singular values will be root of 57 and root of 3. Okay, and then we can form the left and right, right and left, or left and right singular vectors associated with these singular values. And then we say, it says here that the leading eigenvalue, which is the U1, okay, so which is associated also with the eigen, or the eigenvalue, or the singular value with them, with the highest magnitude, gives shows the direction that you see in the scatter plot in figure 2. So it gives the direction of the data. So if we go to figure 2, is this one, okay? So if we have if we plot the scatter diagram of our data, then the first the leading singular value associated with, remember, A transpose is we are looking at the U's. This U1 will give the direction of the data, okay? And actually, I think this singular value will give the spread. I think it's in the next slide. Will give the spread of the data, how much the data deviates from the principal direction. Okay, so then with the most important informations are concentrated in the singular values and the singular vectors. Okay, so we say that SVD of A, that's the centered data, which means that the mean one shows the dominant direction of this in the scatter plot. Okay, and the second singular vector, U2, is perpendicular to U1. Okay, and the second singular value, okay, sigma 2, root of which is approximately root of 3, measures the spread across the dominant line. So like I said, it measures the spread of your data. Okay, so then this is this analysis, or what we call the singular value and as PCA, which is principal component analysis, which is coming from just SVD. So to put everything in one basket, for this case, we have okay, this X, which is coming from A transpose. This is the sample covariance matrix. So we say that the total variance in the data is given by the sum of the singular values. Remember, this is the square root of the eigenvalue. So these are the singular values. Okay, it's a bit confusing, but just bear with me. So that's the sum of the singular values, which is equals to the sum of the trace, or the trace of the diagonal sum, or the x1 and x2s. So yeah, okay, these ones. Okay, the trace. So this total variance, then the principal component analysis is by SVD, saying that the first eigenvector U1 of X points in the most dominant direction of the data. This we have seen. That direction accounts or explains for, so that direction accounts for or explains a fraction of the total variance. So remember that, how do you call it? This gamma sigma 1 square is the highest singular value. So this is this explains most of the data variance. Okay, so this quantity, the sigma 1, explains most of the data variance, and the next eigenvector U2 accounts for the for a smaller fraction. So because sigma 1 is greater than sigma 2, this quantity is greater than this quantity. Okay, and if we go on, let's say if there are some n singular values, then each singular value will account for a smaller and a smaller and a smaller part of the variance. Okay, because one is greater than sigma 2, sigma 3. Okay, so it says stop when the fraction is small. Okay, so this is the part where the PCA comes in, where the principal component analysis comes in. So we have some singular values that are arranged as this: 2 greater than 3 greater than, say, it's up to n. Okay, and then we know that this first singular value accounts for most of the data variance, or so it accounts for most of the data. So most of the information in the data, you can use this singular value to obtain that. If you want to get more, a bit more, this S2 will provide a bit more, and then this will provide a bit more. But then it's going to be such that once you get to, say, sigma I, the information coming from this singular value is so small. Okay, so you can neglect it. Okay, so let's say call this part R. So we take from 1 to R. So we take this the singular value from 1 to R. Then we say that all the information in A can be reconstructed by using the singular value 1 to R. Okay, so information coming from the singular value 1 to R. So this is all that it means by principal component analysis. So, and then we discard from R plus 1 to sigma n. We discard this singular values because it provides almost no information about the metrics. Okay, so just to read through, you have R fractions, R direction is plain. Okay, these U's are the principal components. So the U's associated with so UR U1 to UR associated with the singular values gamma sigma sorry yeah, sigma 1 to sigma R are the principal components. Okay, and we call this R, this stopping criteria, the effective rank of the matrix A. Okay, this is the same thing that they use also in some parts of machine learning and everything. I think they call that a cation or something, a cation or something. So the point is you have some metrics, okay, which will have some singular values. You have some singular values that are arranged up to n. Then you can stop at some point R, and these 1 to R singular values will give you the most information necessary for this matrix A. You can in some cases, in some analysis, you can even pick only the first singular value, and it will give you all the necessary information about this matrix A. Okay, so this is what is principal component analysis. Okay, now let's go back to geoscience. Okay, so the inverse problems, and we look at, so we have seen that our GM equals to D, okay, is given. This is our system. And we have seen that we can decompose our G into the product of three matrices, V transpose. But then, I mean, in reality, what it means is that we have U lambda V transpose times M, okay, equals to D. So we haven't really gone that far yet. Now, what we want is to find G inverse, okay? Which is to find G inverse, and this is the power of where the power of SVD comes in. So if we find if we can decompose G into this, we can decompose G using SVD, then okay, we've already explained where the use and everything is coming from. So let's jump to the inverse. So we are now seeking for some inverse, okay, some inverse operator, G inverse. Then in the case where there are no zero singular values, then G inverse is given by this relation, V transpose inverse lambda inverse and U inverse. Okay, where does this come from? So we know that G is equal to so G is U V gamma or lambda U. Okay, so this is the model space, this is the data space, and if we write this V, okay, divided by the singular values, then we can find that U is also G, okay, which translates into, say, the inverse. Okay, so we have inverse U, okay, and now if we bring U also here, then we have V, okay, because the V hasn't moved, then the the singular values will be this, okay, just a reciprocal, and this is going to be u, okay, so it's going to be u inverse, okay. Now, if we remember that the u's and the v's are octonormal, so then the inverse will be just the transpose, okay. This is where the power comes from. So then the G inverse will be V, and so lambda, I'm just rewriting this, so inverse, and I'll show you what lambda inverse is, and U transpose, okay? So G is given by this, and the inverse of G is given by this, okay? So what it means is that if our estimate will now be given by, because now we can find J inverse for any, this is the thing, for any matrix, we can find the inverse, okay, D. But what this means, we have to explain. And what goes into this lambda to the power minus 1 is the reciprocal of the singular values, okay. So now remember that I'm stating that there are no zero singular values, so all the n singular values are non-zero. Then the reciprocals are defined, okay, so we can find the reciprocals, okay. So then the inverse is given by this relationship, which is here. Now what happens if there are zero singular values? Then you remember that in that case, G actually was decomposed as UP lambda P VP transpose, okay? And in this case, then I think it's on the next slide. Okay, let me just clear this. I shouldn't have cleared. Okay, this is what I have been explaining. So orthogonal matrices. So G inverse is given by this for when none of the singular values are zero. Okay, so in the case where some of the singular values are zero, remember that the singular value decomposition was given by this UP lambda P VP transpose. And then in this case, just like in the case where it's the inverse is given by this relationship. So G inverse is equals to VP lambda P inverse UT, okay. Now this inverse we call the generalized inverse, and this you can find for every matrix. You can find this inverse. It doesn't matter how bad your matrix is, how so singular your matrix is, you can find it. Why? Because even if there are zero singular values, then you kind of use this decomposition. And if there are no non-zero singular values, then you use this decomposition. I think I have a slide about stability and resolution, I think at the very end, but I'll just tag on here that now, let's say, let me just explain something about stability. I think there is a slide, but okay. Let's say you have no zero, you found that none of the singular values are zero. But then say from sigma 1, or let's just say the last singular value, say the last one, okay? It's so small, so it says 0.001. Okay, this is the value of the last singular value. Now, if this is a singular value, now what it means is that if we find the inverse, which is the reciprocal, okay, of 0.001, this value is going to be very, very, very huge. Yeah, because it's just divided by a very small number. And so sometimes there are no non-singular There are no non-singular values. Yeah, but some of them are so small that to make the solution very stable, we have to discard them. Okay, so in these cases, you don't really use singular values that are so small. Why? Because when you take the reciprocal, it's going to appear as a very large number, and this is going to cause so much instability in your solution. So in the case where, even though sometimes there are no zero singular values, we have to discard some of them and use this form. Okay, so we have to set a bound of which singular values are allowed, and we have to use this form of the inverse of G, which we call the generalized inverse operator. So almost all inverse theory it's geared towards finding this generalized inverse operator. I'm just going to just say here there are some things we have to look at, but then remember that we have so once we have the generalized inverse operator, we can find the generalized inverse solution. Inverse D. So today we've looked at say least squares, we've looked at minimum length solutions, we've looked at the weighted and non-weighted cases, and we have looked at the damped least squares, and then now these methods gave us some inverse, and now you have this generalized inverse also to add. So we have three ways of defining the inverse, okay? But sometimes, so before I forget, sometimes even though we can find the SVD, we can find the inverse by SVD, we still have to use the least squares and the minimum length solutions. That's why it's still popular, because of these small because of these the reciprocal, putting the rest because the generalized inverse involves the reciprocal of the singular values. So like I explained, if the singular values are so small, it causes so much instability that you get a better estimate of the model parameters by just using a damped least square solution. Okay, so if you read the seismological books, in the end we talked about some variance of the solution. Yes, this is the most powerful inverse, and you see that you can also reconstruct the the least square. You can also reconstruct the least square and the minimum length inverse solutions from this decomposition. Okay, this is what makes it powerful. We can get the minimum length or least square inverses from analysis of this decomposition. But in the end, we have to go back to just using some damp least square methods because of the instabilities caused by these small singular values. Okay, so that's what we looked at next. We are looking at some measure of quality of the generalized inverse, how good our solution is. So we use some three measures of quality. For the generalized inverse, we define an M by M model resolution R, model resolution matrix R, an N by N data resolution N, matrix N, and an M by N unit covariance matrix called UM. Okay, and what this means is that the model resolution matrix R, it measures the ability of the inverse operator to uniquely determine the estimated model parameters. Okay, so we can measure, you remember when we're looking at the goals of the inverse problem, we can measure how well we are estimating the model parameters. And the data resolution matrix N measures the ability of the inverse operator to uniquely determine the data. So the data resolution matrix gives us which data provides the most information or where most of the the most important information in the data is coming from. We can know that from the data resolution matrix. And the unit covariance matrix is a measure of how uncorrelated noise with unit variance in the data is mapped into uncertainties in the estimated model parameters. So we know that if there are errors in the data, these errors will be mapped into the model parameters. Okay, so what's this relationship? We can also quantify that using the unit model covariance matrix. So these are some measure of quality for the inverse operator. And so we'll see. So let's look at just all these three in a bit more detail. So we look at the model resolution matrix R, and we are trying to find how our estimated model parameters compares with a true model. Okay, so let's say we have a true model. We know, like, true model parameters. We have some model parameters we actually know, and then we measure some data, okay, which gives us some data. Then we use our inverse methods to estimate these model parameters, okay, and then we're finding how this estimated model parameters compares with that. To do that, we remember that G, this is the estimated one, is related to the G inverse and D, but D is coming from the true model, okay? So if we replace D by M true, then we get this. This is the estimated, and then this is the true model. So then the relationship between the estimated model parameters and the true model parameters is coming from this matrix here, okay? That's G inverse G, and we call this matrix R, which is the model resolution matrix. So it's given by G, which is a generalized inverse from the SVD, and then the G itself. Okay, so where R is an M by N symmetric matrix, and we say that if R is equal to the identity matrix, then the estimated model parameters is equal to the true model parameters. Okay, in the case where, and then okay, so then in this case the model parameters are perfectly resolved. Okay, so or uniquely determined by the inverse problem. In the case where R is not the identity matrix, then we say that the estimated model parameters is some weighted average of the true model parameters. Okay, so we can quantify how well we are resolving our model parameters by this model resolution matrix. And then the nice thing is, if we use SVD, then we see that this R, this model resolution matrix, is given by just the VP and VP transpose. Okay, we remember that G is UP. Okay, where in this case, where there are, of course, there are zero singular values. So VP transpose. So we already have VP. So to compute the model resolution matrix, we just find the product of VP transpose. Okay, this is how it comes about, because it's G inverse and G. So it gets here. And then there are other things. We can find the trace of R, the number of non-zero singular values, and some importance. There are some other properties that we can look at of the model that are associated with the model resolution matrix. Okay. Then the data resolution matrix. So in this case, we have some, it goes by the same thing as the R. So the estimated solution given by the inverse estimate, the operator, the estimated inverse operator. We have this model estimates, and this is the inverse operator, and then So this is the true the actual data, the observed data. Then we can predict the the data by G, and using this estimated model based on this estimated inverse. Okay, then we can see that if we replace this G, this is the predicted one. If we replace this M estimated by this, then we have G inverse D. Okay, this is the actual data. This is the predicted data. So it gives us a relationship between the observed and the predicted data. And so this G inverse is the matrix N, which is the data resolution matrix, okay, which finds the link between the predicted and the observed data. So N is the data resolution matrix is given by this, and we say that if N is the identity matrix, then the predicted data equals the observed data, and the observed data can be fit exactly. So the misfit will be 0, okay? And in the case where N is not the identity matrix, the predicted data then is some weighted average of the observed data. So similar analysis to the model resolution matrix. And so again, then N will be, so remember that we were saying that the U and the V, especially when we're here, sorry for going all the way back, the U's are related to the data space, the V's are related to the model space, okay? Here we can see them clearly. So then the data resolution matrix, which is G inverse, is then given by just the data resolution matrix times its transpose, okay? And these are some analysis, also some other importance. But then this is how you compute. Once you find the SVD of G, it's straightforward to find N and R, okay? And now we come to the unit covariance matrix. So it says that any error in the data will be mapped to errors in the estimated model parameters, okay? So let's say that let the errors in the data be delta D, okay? So these are errors. Then the errors in the model parameters due to the errors in the data is given by delta M, which is the errors in the model parameters. And the inverse operator, this is what this inverse operator maps these errors into these model parameters, okay? Now recall that the covariance matrix, the data covariance matrix that we looked at is given by this one. And we can represent this covariance by this average, the data covariance matrix by this, okay? And this is the averaging of the errors in the data. So this is a vector, and this is its transpose. So remember that this is linear algebra. This is an outer product, okay? So this forms a matrix, okay? This is a matrix. So we remember when we're finding the magnitude, it was an inner product. This gives a scalar, but the outer product will give you a matrix. So it goes into the data covariance matrix. And so then in this case, we seek now a model covariance matrix, which is also given by delta M transpose, which is a matrix, okay, which we call the cov M, such that we know the D's are mapping and are being mapped to by the G, okay, G inverse. So here what we're doing here, let's look at this carefully. So G was given delta G and delta G transpose. Okay, so we are trying to map this data covariance using this relationship into the model covariance. And then we see that if we do the transpose operation, this D transpose comes here, and then the G transpose goes to the outside. And then this is in the data covariance matrix. And what's there to say? Okay. So this, okay, it's given by that, and then we can see, we know that this is the covariance, model covariance matrix, and then this is given by the data covariance matrix, and then this is the generalized inverse, okay, so the generalized inverse and the generalized inverse transpose. And so finally, if we define the unit covariance matrix U curve UM. So this is the model covariance matrix, and this is the unit covariance matrix, by assuming that the data covariance matrix is just the identity matrix, okay? Which means that we are assuming that the data variances are all equal to 1, okay? And the covariances are 0. Remember that we have this thing, square, and then xy, okay? So these ones, the diagonal elements are set to 1, and then the off-diagonal elements, that which are the covariances, are at 0. So we have the identity matrix. And then in this case, then the unit covariance, the unit model covariance matrix is then given by G inverse and G inverse transpose. So this, and then this comes from, if we can decompose G using SVD. This is why SVD is nice, because it gives you all these analysis. It's just simply the model space VP, okay, related to the model space, then the singular values. So the reciprocal of the singular value squared, and then VP transpose. So these singular values are squared because we are multiplying two G's here. So you see there is one is coming from here and the other one is coming from here. So this causes this to be squared. So then the unit covariance matrix, it's just these VPs and the columns, and then the diagonal elements where the singular values are squared, the reciprocal, and then we can find V transpose. And this gives us the model covariance matrix, and which is how we determine how the errors which determines how errors or the noises in the data will be mapped into the model estimation. Okay, so now we have some relationship that we can put everything in one place. So we have G, which is coming from our model. Okay, we can use SVD to find the generalized inverse. Then we can, so then G now is given by this, the generalized inverse. This will be our model resolution matrix from the SVD. We can compute this easily. And this will be our data resolution matrix. And this will be our unit covariance matrix, which we compute by that. So as a quick example, how do we compute all these things? So let's say we have our system, which is given by this matrix, and our we have to find two model parameters, and this is the data, okay, 2 and 4.10. Then once we do all the G transpose G and all the analysis, we find that the singular values will find two singular value decomposition finds these two singular values. Okay. Before we go there, I think it's somewhere in the slide. I'm running out of time, so I'm just going to say that note this singular value. It's so small, very small, such that when you find the reciprocal, it's going to cause a huge amount of trouble. Okay. Anyway, let's go on. So, and then we can find UP, VP as these matrices. And then once we find this UP, VP, we can compute the model resolution matrix. where in this case is the identity matrix. And remember that in this case, it means that we can really predict the data exactly, estimate the model parameters exactly, and also the data resolution matrix is also the identity, so we can predict the data exactly. So I mean, we're going to get an exact solution, but then we'll see. And then G inverse will be given by, is given by this matrix, and then the estimate of the model parameters will be G inverse times the data, which is coming from here, and then that. And then we see that we're getting -8 for the first model parameter, and then 10 for the second model parameter. And the unit covariance matrix, which is given by this, will be, so VP, VP transpose. Now look at this. This is 1 over the square, the reciprocal of the square of the first singular value. But look at this value here. This is a huge value, 100,000 something plus. So then this then maps so that our unit covariance matrix is this here. So what it means is that this is the variance in our data, okay? So it's associated with the variance in the data, the two data, and this is this off diagonal is the covariance. So these are so it's like it's really correlated, okay? So there is a huge correlation between the two data. So there is a simple analysis where in this, if you have a unit covariance matrix as this, then you should know that you have a problem with your model estimation, which can be seen because this is coming from remember I said about the instability due to the caused by the small singular values, okay? This is what is causing these huge numbers here. So then it's so, we say that this system is so sensitive to the noises in data, which we can see by changing the D2 to 4.0 instead of 4.1, okay? Here we're using 4.1. If we change to 4.0, then our new estimate of the model parameters will be 2 and 0. Before it was -8 and 10, okay? So it's like a very huge difference just by changing by putting a 2.5% error. You have this huge difference. In the case where it's stable, it should be, if you add this amount of noise, you should be getting something around, say, 8.7, say, I don't know, 9.2. Okay, so it should be around the actual solution, the previous solution. Then we say that the system is a bit stable. But look at this jump. It's a clear indication that your system is really unstable and it's so sensitive to noise. So these are how you quantify or classify or estimate how well you are resolving your model parameters by these analysis. So this is the resolution versus stability. This is what I talked about before. It's the same thing and it's the same problem. If we now given by the same thing, the point here is that although in the case where we consider the whole system, we consider these two singular values. Our resolution matrix was the identity matrix, our data resolution matrix, our model resolution matrix, sorry, and our data resolution matrix were both the identity. So we can resolve both the model parameters and the data exactly. But then we saw that this system is quite really unstable and very sensitive to noise. So then the point is, if we should discard one of these singular values. So we set lambda 2, which is almost 0 to 0. Okay, so that in this case we will neglect the other how do you call it? The singular vectors associated with lambda 2. Then UP and VP becomes just a vector, okay? And then we can see that the model resolution VP times VP transpose is just, now it's not the identity matrix, but it's given by this square matrix, which means that we are resolved. So what these values are the same, which means that we are both model parameters are equally resolved, okay? Whilst in the case of the data resolution matrix, it changes to 0.2 to 0.8. So what it means is that, so remember it was some combination of the data. So it means that the second data is the most important, okay, because D1, D2, and then D2, this vector is a linear combination. So this D1 will take this column, this D2 will take this column. So what this model resolution, data resolution matrix is telling me is that the second data is the most important in my analysis, okay? Whilst here, all the two model parameters are equally resolved, okay? In some analysis, probably we'll see on Wednesday when we do tomography, we'll get different values, and then it tells you which values are well resolved and which ones you don't have to trust that much, okay? So this is the resolution analysis. And then in this case, our G inverse will be this matrix, and unit covariance matrix will now be well behaved, okay? So these are the variances. In this case, these are the variances, and then these are the covariance, which it's reasonable. Now, if we should compute G, okay, this will be the solutions, and then this will be, you see that once we use this estimate to predict the data is closer to the observed data. Remember, the observed data was 4.1, okay? And so yeah, these are some of the analysis you do. So yeah, that's it for today. And there are some things I wanted to explain, but probably I'll send you these emails, and then we can discuss them tomorrow, because I wanted you to write some code for just doing this nonlinear example, to linearize some nonlinear example of, I think, earthquake locations and everything, but I need to explain to you, so probably tomorrow. Okay. What codes do you write? What do you call it? MATLAB or Python or whatever? Hello.
Hi.
Yeah, hello.
Yeah. What do you write? You write MATLAB, Python?
I think,
which one do you guys feel comfortable in?
I think I mean both of them, Python
Okay.
or
So we can do some exercises about these inverse problems. But okay, so this ends today's lecture. Please, questions about the second part about the SVDs and everything. Question time. Any questions, please?
We don't have questions for now.
Oh, you guys were sleeping?
No, we are awake.
Everything is clear? Well, I mean, okay, no questions, but is everything clear?
Yeah, we hope.
How many people are here now?
I think we need to go
Yeah,
through.
yeah.
If we discover some questions, we will contact you soon.
Okay, okay. So I'll send you this what do you call it, PPT, and some materials, especially the lectures I picked all these things from, so you can read the whole thing. And then yeah, but this is important. You have to understand these things and many more. I mean, there are more to it, but not too far from this because we didn't even do the continuous case. This is just discrete, you know, linear, mostly linear relationship. There is the continuous case, and then there is the statistical or Bayesian cases. But I mean, these are things you looked at in your PhD or when you do some masters or some other programs, but okay, or even your project. So, okay, then if there are no questions or further comments, then we end today's section, and I'll see you guys tomorrow.
Okay.
Okay.
Thank you.
Thank you so much.
Thank you.
Okay, now how do I stop this? My screen is still sharing, no?
No.
Oh, okay. Well,
Not
in
sure.
any case, I can leave the meeting. Okay, ciao.
Ciao.
Ciao, bye.